Next we are going to start nomenclature of aromatic compounds. Aromatic. The word aroma means which has got a characteristic smell. That means this compound has got some or other smell. Alright? So hence it is called aromatic. Now this is also being called as arenes. This is also known as. I have told you when I started the chapter nomenclature that at that time I said you arenes. Arenes is again same thing. AR has come from the word aromatic and ENE because you will find that arenes, in arenes we are having benzene. So we have alternately single and double bond. Single and double bond. Double bond is known as what? In. So hence it is known as arenes. We can say that. ENE. AR has come from the word aromatic and ENE, as you can see there, alternately single and double bond is there. Hence we call it as arenes. So aromatic compounds are otherwise also known as arenes. We can say that. Okay, fine. So in this way, what I find is that we are going to study the nomenclature of these aromatic compounds. That is, it's very important, nomenclature of aromatic compounds, because already we have completed that is aliphatic, alicyclic, and finally we are coming to aromatic. Now, aromatic compounds, when it came into being, when we came to know about the aromatic compounds, different scientists gave different structures about this aromatic ring that we are going to study when I teach you hydrocarbons. When I will start the chapter hydrocarbons, this is nomenclature I am teaching you. When I will start the chapter of hydrocarbons, hydrocarbon means I will be teaching alkanes, alkenes, alkynes, benzene. When I do benzene, sorry, at that time I will tell you about the history of the aromatic compounds, what are the structures given by the different scientists. Little bit just I want to tell you because otherwise you won't understand from where we got this particular structure. Now this structure was given by Kekulé. A scientist was there whose name was Kekulé. He gave this particular structure. Alright, he numbered it in this way. That is 1, 2, 3, 4, 5, 6. Either we can write this or we can also write. Now this is equivalent sign, you know that. Alright, we can also write in this way. We can also write in this way. So that is 1, 2, 3, 4, 5, 6. I told you by default we take this as the first position. By default. Otherwise anyone you can take as the first carbon atom. Anyone. By default we take this as the first carbon atom. Now here what you can say is that Kekulé said that we can write the benzene structure in this way or in this way. Kekulé said we can write the benzene ring. Either we can represent in this way or in this way. But this structure has got certain disadvantages. Now let me tell you, before Kekulé also many scientists was there, which I said you that I will be telling you in hydrocarbons. When I teach you hydrocarbons, at that time I will say you that who are the scientists and what they said about it. But their structure was discarded and Kekulé's structure was being considered because Kekulé was the first scientist who said that benzene is two-dimensional in nature. Two-dimensional benzene is. Otherwise, everybody said that benzene is three-dimensional, which is absolutely wrong. For that reason, it was discarded. Alright, there are other reasons also, but that is one of the main reasons. We can say that they considered that benzene to be as three-dimensional. All other scientists. Alright, only Kekulé was the first person. Kekulé was the first scientist who gave the structure of benzene, and he only considered that benzene as two-dimensional in nature. But what he did is that he gave two structures to you. So you can see structure 1 and structure 2. And in structure 1 and 2, he said that we can put the double bond in the first and the second carbon atom also, and we can put the double bond in the first, in second and third also we can put it, and alternately we can represent the structure in this way or we can represent the structure in this way. Both are correct. Now, okay, according to Kekulé, he is correct. But later on, when the aromatic, what you can say, hydrocarbon progressed, the people came to know more and more about it. Then we came to know whatever the structure given by Kekulé was having some drawbacks. It was. I don't say that it was completely discarded like the previous scientist, but it has got some drawbacks. Still, we use this particular structure today. Still, we are using it. Got it? But it has got some drawbacks. So, what is the drawback? It is in front of you only. You can see that. In the first structure, if you see, then what you find is that the first carbon, first and second carbon, between the first and second carbon, there is a double bond. And here between the first and second carbon, there is a single bond. So, if a particular student is writing the reactions between the first and second carbon, he will undergo addition reactions because double bond is there. You know that double bond undergoes addition reactions. Multiple bond, double and triple bond undergoes addition reactions. You have studied in the lower classes. Okay? Multiple bonds. But if another student, he is writing this structure and if he is writing the reactions, then he will do substitution reactions between the first and second carbon atom. Why? Because single bond is there. Single bond undergoes substitution reaction and double and triple bond undergoes addition reactions. So if a person is writing, if a student is writing this structure and he is doing addition reaction, he is correct. If a student is writing this structure and he is doing substitution reaction, he is also correct. How it is possible? That the same compound will give they will give addition reaction as well as substitution reaction. How it is possible? It's not possible. Addition and substitution both are completely different. Because this is saturated, so to say, and this is unsaturated. How it is possible that in one structure it is benzene is unsaturated, in another structure benzene is saturated? No, not possible at all. Alright. The next thing is that Kekule could not say anything about the stability of the benzene ring, that whether these rings are stable or not. Now stability, how do we calculate? By calculating the energy. Because remember it, what I am saying you. Energy is inversely proportional to stability for any compound. In chemistry, how do we compare the stability? We compare the energy. Energy is less, stability is more. Energy is more, stability is less. Now how can we say that? It's a very simple thing you see. Suppose a stone is there at the top of the hill. How do we calculate the energy of the stone? Potential energy, mgh. It's maximum. But when the same stone is at the bottom of the hill, you calculate the potential energy, mgh. Now h is almost zero, nil, negligible. So energy is what? Minimum. So stability is what? Maximum. Because when the stone is at the top of the hill, it has got every chances that it will roll down the hill by giving a slight push. Slightly you push it, it is going to roll down the hill. It has got every chances. That means it is highly unstable in nature. Try to understand. So hence it is highly unstable in nature because energy is maximum. What I said, mgh, height is maximum, so energy is maximum, stability is minimum. But when it is at the bottom of the hill, height is minimum. Height is minimum, so energy is also minimum. mgh you calculate, it is minimum, but stability is maximum. If you give a slight push to the stone, what will happen? Will it roll down? Where it will roll down? Because it is already at the base, it is already at the bottom of the hill. It is going to slide from this position to that position. It will slide. It's not going to roll down. It's going to slide. Change its position. That's it. So what do you find? When energy is minimum, stability is maximum. Always remember this particular thing. Alright, it's the same thing in the case of compound also. When the compound is having minimum energy, it has got maximum stability. So Kekule could not calculate the energy of the benzene ring. He could not calculate. He gave the structure. He gave the structure two-dimensional, but he could not say anything about the stability of the benzene ring because he could not calculate the energy of the benzene ring. Alright, he could not say. Next is, Kekule said that benzene undergoes addition reactions, but later on we found it out experimentally that benzene neither undergoes addition reaction nor it undergoes substitution reaction. It undergoes electrophilic substitution reaction, a different type of reaction. We will be studying it. I will be teaching you. It undergoes. Then, so hence, still some more are there which we will be studying in that particular chapter, hydrocarbons. So hence, what we find is that for that particular purpose, his structure was not completely discarded. Alright, but we came to another structure which was given by a group of scientists, and this structure is known as resonance. Now don't think resonance is the name of a scientist, listen carefully. I said a group of scientists. Alright, this is a resonance structure. We are putting a ring inside it. Instead of alternately single and double bond, we are putting a ring. How do we come to ring? All these things I said you. Have patience. When I will teach you the hydrocarbons chapter, you will come to know how did we get this particular ring. Alright, clear, I will say you. So this structure is known as a resonance structure of benzene. It gives us all the information about the benzene ring. It gives us the stability of the benzene ring. It says that benzene undergoes electrophilic substitution reaction. How benzene is stable, it also explains about it. Alright, so hence this structure we consider to be as correct, which is given by resonance, and we consider what I said, this is a resonance structure of benzene. We consider that. This is a resonance structure of benzene, which gives us all the informations, or rather I should say, what are the information Kekule could not give it to us, or the Kekule gave the information which was not correct, that was provided by resonance. Alright, and hence this structure is correct, and we are having this structure today, that is the resonance structure of benzene. We can say that. And it's easy to write also. Here we have to count it and see alternately single and double bond. Here no need to count it, just you make a hexagon and put a ring inside. It's very easy to represent. So it is the benzene ring. So hence we will be representing the benzene ring in this particular manner. You can represent in this way also, it is not wrong. Still we are using it. While doing the mechanism of reaction, we use this one only. We don't use this, we use this because it is easy for us to show the shifting of the bond. You will come to know about it. Of the shifting of the bond, you will come to know when you will study the GOC. GOC means General Organic Chemistry. That's it, yes. Where you will study about the organic reaction mechanism. At that time, you will come to know. Okay, a lot of things are there to be studied. Hence, children, for that reason, I say that give what you can say 100% to your studies because a lot of things are there to be learned. Okay, fine, understood now. So hence I'll be using this particular structure, the resonance structure of the benzene, and tell you the different structures of benzene. Okay, so just a brief idea I gave it to you that from where we got this structure and why do we have this particular structure. Okay, a brief idea I gave it to you. Again I repeat, I'll tell you more about it in hydrocarbon chapter because this is nomenclature. This is not my chapter now where I should speak about benzene, we can say that, because I need to understand the naming first. Naming, I am studying about the naming. So now as you can see, this is your benzene ring. Now benzene has got two type of structures. One is nuclear derivatives and another is your side chain derivatives. Alright, listen carefully. We have got two type of structures. One is nuclear derivatives. What I said? Nuclear derivatives. Nuclear derivatives. Another is your side chain derivatives. Side chain derivatives. Okay. Now, side chain means what? And nuclear means what? Now listen carefully. When the functional group is directly attached to the benzene ring, directly, like OH, is directly attached to the benzene ring, you can see it is known as nuclear derivatives. When the functional group, whether it is OH, whether it is COOH, whether it is CHO, whether it is CO, whatever it is, any functional group which is directly attached to the benzene ring, it is known as nuclear derivatives. But if the same functional groups are attached to the side chain, like suppose we are having CH2OH, it is not attached directly. This OH is not attached directly to the benzene ring. It is attached to a side chain. That is known as what? Side chain derivatives. Hence it is called as side chain derivatives. And the naming is also being done differently. Alright, naming is also done differently. So how to name it? Okay, in the next day we will see. Thank you.